Today we're going to talk about design aids in AISC. There are quite a few design aids for bending. And recall that on Wednesday we analyzed a W21/48 as part of the local buckling lecture. We found our local buckling lambda P and lambda R values using the equations that are found in our AISC Waffle House menu, which is actually table B 4.1-B, which gives pictures of the various sections and then their corresponding equation. Based on the lambda for the flange and the web, we determined that the flange was non-compact, but the web was compact. But now if we look at table 1.1 for the W21/48, we see that it has a superscript F, which indicates that it is non-compact for flexure for the preferred material specification. So this is the first and simplest design aid. If we scan through table 1.1, what we're going to find is that very few rolled sections are actually non-compact. And there's a good reason for this. Rolled sections are designed and engineered by the manufacturers to be trouble-free, compact members. For ordinary design, in other words, we are not usually concerned about local buckling, and very few members are actually susceptible to local buckling. So why do we even study local buckling? We generally study local buckling because built-up members, that is, members that are made from individual plates, not rolled shapes that are stock and from the manual, these sorts of shapes are commonly used in highway applications and often contain non-compact and slender elements. So then on Wednesday we determined that with a non-compact flange, we could compute the nominal moment capacity Mn for the W21/48 by linear interpolation. Converting this to kip feet and then including our omega safety factor, we get an Mn over omega of 265 kip feet. Note that is slightly less than the Mp over omega, which is 267 kip feet. Now referring to table 3.2, we see that the AISC manual actually reports an Mp over omega for a 21/48 of 265 kip feet. And what this tells us is that table 3.2, while it says Mp over omega, this really represents the Mn over omega considering local buckling. Why does AISC do this? It seems that they're reporting a little bit of a lie. Well, they do it because if we know that LTB can't happen, which is often the case, then this 265 value is the limiting allowable moment for the W21/48. But the great thing about this is that we now know that table 3.2 accounts for local buckling. And this is a big deal. It means that you don't actually have to do local buckling calculations for rolled shapes that are in the manual in table 3.2. Next, let's consider an LTB chart. This is a graph of the allowable moment, Mn over omega, versus the unbraced length. I've used Excel, and I've incorporated the AISC equations for two different rolled shapes. So you can see the three different ranges: plastic, inelastic, and elastic lateral torsional buckling. Note that the W21/55 is a better bending member when the unbraced length is small, but the W12/79 is a better bending member when the unbraced length is large. Now I have a brilliant business idea for this class. Knowing how cumbersome it can be to perform LTB calculations, including the interpolation, or worse yet, executing the plugging and chugging of the elastic LTB equation, you can probably appreciate that some engineers would love it if someone were to put all of these LTB equations into Excel and plot out graphs just like the one you're looking at, but for every single section in the steel manual. I think engineers would kill for this. I think this idea is worth millions. We would produce charts. For example, if you knew the applied moment was 280 foot kips and that the unbraced length was 15 feet, all you would have to do is select a shape that is stronger than that position. You would see that for 280 foot kips and an unbraced length of 15, the W21/55 is not quite adequate. It only has a strength of about 220. So it's not adequate, but the W12/79 is adequate with a strength of 280 with an LB of 15 feet. Well, unfortunately, the business idea is not going to pan out because AISC started doing this about 50 years ago. Table 3-10 shows every wide flange shape and its Mn over omega versus the unbraced length. With green values for ASD and blue values for LRFD, we can pick out the LTB curve for any shape, show its plastic, inelastic, and elastic ranges as they continue from page to page within the book. So if you piece together multiple pages, you can follow the strength of a particular shape as it decreases with increasing unbraced length. So in red and black, here are the two shapes that I had previously graphed. So here's a simple example. Our job is to pick the lightest A992W shape with an applied moment of 310 foot kips, an unbraced length of 20 feet, and the CB factor equal to 1. Locating page 3-122, I show the moment strength of 310 that I need at an unbraced length of 20 feet. Then I find that a W18/76 is the lightest shape that has a moment strength above 310 at a length of 20 feet. I know that it's adequate because at 20 feet it has a moment strength above 310, and I know that it's the lightest because AISC makes the solid lines the lightest section and the dashed lines the sections that are actually heavier. So all I need to do is pick the solid line, and I have the lightest shape that meets the criteria. So now in example 2, I have to pick a shape for a center point applied load of 40 kips. The unbraced length is 9 feet with an overall span of 18 feet. A handy design aid is table 3.1, which gives CB values for some of the most common simply supported beams. So using this, I don't have to compute CB. I find the correct condition and it shows me that CB is equal to 1.67. I know that I need an allowable moment of at least 180 kip feet because the reaction would be 20 kips and the distance from the support to the maximum moment point would be 9 feet, giving me 180 kip feet. Intersecting the required moment of 180 with the unbraced length of 9 feet, I find that a 16 by 45 is adequate. However, I think a 16 by 40 might actually be adequate. The reason I think this is I haven't yet considered the CB factor. Now remember, the CB factor increases the LTB strength of the beam. Of course, it has no effect on the plastic strength. Now these charts have been made for a CB factor of 1. That means that my real allowable moment for a 16 by 40 is actually 159 times the CB factor of 1.67, or 266 kip feet. Still, that's not the actual allowable moment strength because we can never exceed the plastic moment strength. So based on the plastic moment, the allowable moment will be 182.5. Or in other words, the CB factor has increased the LTB strength so that LTB will not occur, and the controlling moment is 182.5. Since 182.5 is greater than the applied moment of 180, I believe a 16 by 40 will work, but now I'll check the self-weight. Including self-weight, my applied moment is 181.6, so I conclude that a 16 by 40 is adequate. So now let's talk about these awesome design aids and what their limitations are. The LTB charts basically cover everything. Plastic, LTB, and local buckling are all considered, but of course they have limitations. Fy must be equal to the preferred material specification, which would mean Fy is equal to 50 for W shapes, and they're only applicable to W and C shapes. So be careful if your professor gives you problems in which Fy is not the preferred material specification. And I would further comment that though the LTB charts are great because they contain everything, they can be a little cumbersome to use for the fairly simple problem. For example, problems that definitely don't involve LTB. For the simpler problems, you might prefer the Z-tables. Actually include both plastic and local buckling. And further, remember, local buckling rarely occurs in rolled shapes. And we know that the only shapes that are going to have local buckling are those that in the manual clearly have a superscript that says F. If it doesn't have a superscript that says F, local buckling doesn't happen. But again, if it does happen, these Z-tables take it into account anyway. And the tables have limitations. These are going to be for the preferred material specifications, and they're really only for W and C shape. So be aware your professor might give you problems that are just not W shapes. They might be S shapes. In that case, you're not going to be able to get any help from the Z tables.